Good morning, everyone. Myself Muskan. I am from B.Sc Chemistry Honors third year. My roll number is 54. Today, I am going to make an audio recording lecture for visual impaired students on topic physical properties and molecular structure of physical chemistry by Dr. S.C. Khetarpal. Introduction. The various methods used for study of molecular structure may be broadly classified into the following two types. Number 1. Methods based upon the study of physical properties of the substance such as first point molar refraction, second point paracore based upon surface tension, number 3 optical activity, number 4 dipole moment, number 5 magnetic susceptibility. Second point spectroscopic methods such as number 1 rotational and vibrational spectroscopy, microwave and infrared spectroscopy. Number 2 electronic spectroscopy, UV and visible spectroscopy. Number 3 Raman spectroscopy. Number 4 nuclear magnetic resonance NMR spectroscopy. The study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as that property the total volume of which is the sum of which the values of its constituent atoms. A constitutive property of a molecule is defined as that property which depends upon the constitution of the molecules, that is, arrangement of atoms within the molecule and the presence of multiple bonds, rings, etc. in the molecule. Spectroscopic methods have already been discussed in chapter 3. Now, in this chapter, we shall take up a brief discussion of three important physical properties, namely optical activity, dipole moment, and magnetic susceptibility, one by one. Optical activity. Definition. Number 1 plane polarized light. If a ray of light travels in any direction, it has vibrations in all directions at right angles to the path of propagation. If this light is passed through Nicol prism, then the light. A Nicol prism consists of two prisms joined together. Each of these prisms is made out of a substance called Iceland spar or calcite, which is mainly CaCO3. If a single prism is used, it is found that two beams of light come out, each of which is plane polarized, and the planes of the two are at right angles to each other. By combining with second prism, one of the beams undergo total internal reflection and only one plane polarized beams comes out. Instead of nickel prism, a polaroid is also sometimes used. It consists of a film of cellulose acetate mounted between two glass plates, which emerges out of the prism is found to have vibrations only in one plane. This light is called plane polarized light. The nickel prism thus used is called a polarizer. Second, optical activity. If the plane polarized light is passed through a plate of quartz or turpentine oil or the solution of sugar, it is found that in the light that comes out, the plane of the polarized light get rotated. The substance like quartz, sugar, etc., which rotate the plane of the polarized light, are called optically active substances, and the property of a substance to rotate the plane of the polarized light is called optical activity. The substances which rotate the plane of the polarized light to the right are called dextrorotatory, and those which rotate the plane of the polarized light to the left are called levorotatory. Latin levus is equals to left. The method of observing the rotation of plane of the polarized light is based upon the following principle. If the plane polarized light is passed through another nickel prism which has its axis parallel to that of first nickel prism, the light passes through and brightness is observed through the eyepiece. On the other hand, if the second nickel prism is placed with its axis at right angles to that of the first prism called crossed position, the light is completely cut off and field of view in the eyepiece is dark. At all other positions, the brightness is less, but there may not be complete darkness. It is observed that if two nickel prisms are set at the crossed position so that the field of view is completely dark, and then the optically active substance is placed between the two prisms, the field of view becomes somewhat bright. The second prism has to be rotated through certain angle about the line of propagation of light to get complete darkness again. This clearly shows that after passing through the optically active substance, the plane of the polarized light has been rotated. The degree of rotation depends upon the rotation required to be given to the second nickel prism to get the darkness again. Thus, just as the first prism polarizes the light and is called polarizer, the second prism analyzes the light and its specific rotation. Number 3. The angle in degrees through which the plane of the polarized light is rotated on passing through the solution of an optically active substance depends upon the following factors. Number 1. Nature of the optically active substance. Number 2. Concentration of the solution in gram milligram. Number 3. Length of the solution, that is the length of the tube through which the light passes. Number 4. Wavelength of the light used. Number 5. Temperature of the solution. Thus, if m grams of the substance are dissolved in V ml of the solution, so that the concentration of the solution is m by V gram per ml. L is the length of the tube in decimeters and alpha is the angle of rotation in degrees. Then it is found that alpha is directly proportional to concentration in gram per milliliter into length of the cube in dm. Lambda is directly proportional. Alpha is directly proportional to m by v into L. Alpha is equals to alpha t lambda m into L upon V, where alpha t lambda is a constant characteristic of the nature of the substance and depends upon the wavelength of light used and the temperature of the solution T degree Celsius. If D line is of the sodium vapor lamp light is used and the temperature of the sodium is 25 degrees Celsius, then it is written as alpha 25 degree D. This constant is called specific rotation of the substance. Thus, from the above equation, alpha is equals to V into alpha upon L into M. Now, if M is equals to 1 gram, V is equals to 1 ml and L is equals to 1 dm, then alpha is equals to alpha. Hence, specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of the substance is dissolved in 1 ml of the solution. Concentration of the solution is 1 gram per ml and the length of the solution through which light passes in 1 dm. In all reported value of alpha T the concentration of the solution is taken in grams per 100 ml of the solution. Thus, if C grams are dissolved in 100 ml of the solution, then we may put M is equals to C and V is equals to 100. This gives from equation 2. Alpha T lambda is equals to 100 into alpha upon L into C for solution, equation 3. Further, if instead of solution substance takes is a pure liquid or a solid, then M by V is replaced by density D of the pure substance. This gives from equation 2. Alpha is equals to alpha upon L into D for pure liquids or solids. In case of a pure solid, L is taken as the thickness of solid in dm. Number 4. Molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight m of the substance and dividing the result by 100 to reduce the magnitude of the number. It is usually represented as m t lambda, thus m power में t lambda is equals to m alpha t lambda upon 100. Measurement of optical activity, that is the angle of rotation alpha. The instrument used for the measurement of the amount of rotation caused by an optically active substance to the plane of the polarized light is called a polarimeter. The principle of this instrument has already been discussed. The principle of the instrument has already been discussed. It consists essentially of two nickel prisms, one called the polarizer and the other called the analyzer. Both of these are fitted on the opposite ends of the same metal tube. However, the polarizer is fixed, but the analyzer can be rotated about the axis of the tube in between the polarizer and the analyzer. There is a space for keeping the glass tube containing the solution. The glass tube is usually 5 cm, 10 cm, 20 cm or 25 cm and has glass windows on both ends. A circular scale is fixed on the metal tube. In the procedure, first of all, monochromatic light from a suitable source, usually sodium vapor lamp, is passed through the instrument without placing the tube containing the liquid or the solution. The light emerging out of the analyzer is viewed through the eyepiece. The analyzer is then rotated slowly till the field of view is completely dark. This gives the initial reading of the instrument. Now the tube containing the liquid or the solution of known concentration is placed and the shutter closed. On seeing through the eyepiece, the field of the view is no longer found to be dark. The analyzer is rotated slowly till the field of the view is completely dark again. This gives the final reading. The difference between the final reading and the initial reading gives the angle of rotation alpha. If it comes out to be positive, the substance is dextrorotatory, and if negative, it is levorotatory. Modern instruments have numerous improvements over the simple type. However, the basic principle remains the same. Optical activity and chemical constitution. Optical activity is a purely constitutive property, that is, it depends upon the arrangement of atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which four different atoms or group are attached. Such a carbon atom is called an asymmetric carbon atom and is usually shown by putting a sign of star over it. A very simple example of such a compound is that of lactic acid as represented below. It is found that such a compound exists in two forms, one of which rotate the plane of the polarized light to the right and is called dextrorotatory D form or plus form, and the other which rotates the plane of the polarized light to the left and is called levorotatory L form or minus form. The two forms have the same constitution, that is, in each form the asymmetric carbon atom is attached to the same four atoms or groups, but differ in their configuration, that is, arrangement of atoms or groups in space. Thus, the two forms are space isomers called optical isomers. Lebel and von Hoff pointed out the difference in the two forms by suggesting that in case of such molecules, the asymmetric carbon atom is present in the center of a regular tetrahedron and the four atoms or groups attached to it are present at the corner of the tetrahedron. This gives rise to two different spatial arrangements which were like the mirror image of each other. The above two configurations are different in the sense that they are not superimposable over each other. Thus, the two forms are related to each other as the right hand is to the left hand of the same person. In form 1, the arrangement form H to OH is clockwise, and in form 2 the arrangement form H to OH is anticlockwise. Hence, if one of them is dextrorotatory, the other is levorotatory. However, by mere inspection of the configuration, it is not possible to predict as to which form is dextro or levo. The two forms are said to be enantiomorphs. Greek enantio is equals to opposite, morphe is equals to form. Further, if equimolar quantities of the two forms are mixed together, a third form is obtained which is optically inactive. This is obviously due to the fact that the rotation caused by one form to the right is nullified or compensated by the equal rotation caused by the second form to the left. This process is called external compensation, and the substances thus obtained are called racemic mixture or DL form or plus minus form. This form can be separated into D and L form by suitable methods. In case of compounds containing two asymmetric carbon atoms, example tartaric acid, a fourth form is also found to exist. In this form, the rotation caused by the half of the molecule is compensated by the other half within the molecule as shown for tartaric acid. This form, which is optically inactive due to internal compensation, is called mesoform. Lastly, it may be mentioned that optically activity is found not only in the organic compounds containing an asymmetric carbon atom but also in the compounds which contain other asymmetric atoms like nitrogen, sulfur, silicon, cobalt, tin, etc. Further, some compounds may not contain an asymmetric atom but are optically active because the molecules as a whole is asymmetric. That is, no plane can divide the molecule into two identical halves. Thus, it may be concluded that the optically activity is a property related with asymmetry of the molecules. Hence, optically activity can be used to test the presence of asymmetric in the molecule. Dipole moment. General introduction. Number 1. Polar and non-polar covalent bonds. A covalent bond is formed by the mutual sharing of electron between two atoms. If the two atoms are identical, example in H2 or Cl2, etc., the shared pair of electron is attracted equally by both the atoms and hence it remains exactly in the center of the two atoms as shown below. H exactly in the center, Cl exactly in the center. Thus, neither of the two atoms in such molecules acquires positive or negative charge. The bond thus formed between two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, example in the HCl molecule, chlorine atom is more electronegative than the hydrogen atom. Hence, the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electron is more displaced towards the chlorine atom than towards hydrogen. As a result, the chlorine end of the molecule acquires a slight negative charge while the hydrogen end of the molecule acquires a slight positive charge. The bond thus formed between the two dissimilar atoms having slightly different electronegativities is called a polar covalent bond and the molecule is called a dipole. Because it has developed positive and negative poles, thus the situation in HCl may be represented as Number 2. Dipole moment of a diatomic molecule. The extent of polarity or polarization of a molecule is expressed in terms of dipole moment, which is defined as follows. The dipole moment of a polar diatomic molecule is the product of the charge on each end of the molecule and the average distance between the centers of their nuclei, that is the bond length. In general, for a polar diatomic molecule AB in which atom B is more electronegative than A, if positive Q plus Q is the charge on the end A and minus Q on the end B of the molecule and D is the average distance between the centers of their nuclei, then the dipole moment of the molecule AB is given by mu is equals to Q into D. Obviously, if the molecule is non-polar, Q is equals to 0 and hence mu is equals to 0. Number 3. Units of dipole moments. The The charge present on the ends of the molecule is usually of the order of 10 raised to power minus 10 ESU, and the distance between the atoms is usually the order of 10 raised to power minus 8, that is angstrom unit. Therefore, mu must be of the order of 10 raised to power minus 10 into 10 raised to power minus 8 is equals to 10 raised to power minus 18 ESU centimeter. This value is called 1 dBi after the name of the pioneer worker in the field. Thus, 1 dBi is equals to 10 raised to power minus 18 ESU centimeter. Number 4. Vector nature of the dipole moment. The dipole moment is a vector quantity, that is, it has both magnitude as well as direction. It is therefore represented by the arrow pointing from the positive end to the negative end of the molecule. Number 5. Dipole moment of a polyatomic molecule. In a polyatomic molecule containing more than two atoms, every two bonded atoms have their dipole moment. This is called the bond moment. The net dipole moment of the polyatomic molecule is the resultant of the different bond at moments. Obviously, the resultant will depend upon the direction of the bonds. Thus, if a molecule AB2 contains two AB bonds at an angle of theta and mu AB is the value of each bond moment, then the dipole moment of the molecule will be mu is equals to 2 mu AB cos theta star upon 2. As mu is known from experiments, therefore knowing the value of theta, the method is usually used for the calculation of bond moments. Alternatively, knowing the value of mu and mu AB, the method can be used for the calculation of theta and hence for predicting the shapes of molecules. The resultant dipole moments of the groups like NO2, NH2, CH3, etc. have also been reported. These are called group moments. Their values depends upon whether the group is attached to an alkyl radical or an aryl radical. The values of a few groups are given below. Group X NO2 group moment in ALK X 3 minus 3.05. A negative value of the group moment means that the group is more electronegative, and a positive value means that the group is less electronegative than the alkyl or aryl radical benzene ring. Electrical polarization of molecule. Every molecule is made up of positively charged nuclei and negatively charged electron cloud. The center of positive charge coincides with the center of negative charges. Hence, when such a molecule is introduced between the two plates of an electric field, the positively charged nuclei and hence the center of positively charged is attached towards the negative plate, whereas the negatively charged electron cloud is attracted towards the positively charged plate of the electron field. As a result, the molecule gets distorted as shown. This is called polarization of the molecule, and the distorted molecule with positive and negative ends is called an electric dipole or dielectric. The molecule remains polarized so long as the electric field is applied, but goes back to the original state as soon as the electric field is switched off. That is why this type of polarization is called induced polarization, and the electric dipole formed is called induced dipole. Since even after polarization the molecule is neutral as a whole, this means that the positive charge on one end must be equal to the negative charge on the other. Suppose this charge is Q. If D is the distance of separation between the charges, then dipole moment of induced dipole, called induced dipole moment, represented by mu I, will be given by mu I is equals to Q into D, first equation. Evidently, the value of mu I will depend upon the nature of the molecule and the strength of the electric field. Say X, we write mu1 is equals to alpha into X, second equation, where alpha is a constant and is called polarizability of the given molecule. Alpha is further found to be related to the dielectric constant D of the medium present between the plates, that is, the molecules being studied. According to the equation, put forward by Clausius and Mosotti. D minus 1 upon d plus 2 into m upon mu rho is equals to 4 by 3 pi n alpha. Equation 3, where m is the molecular mass of the molecule, rho is the density of the molecule, n is Avogadro's number. Clausius-Mosotti equation. Suppose an electrostatic field is applied to two plates so that they are charged. Suppose the strength of the uniform electric field produced between them is equals to E naught. Now, if a non-polar molecule medium is placed between the plates, the strength of the electric field will be reduced to E because the induced dipole called dielectrics act in opposition to the applied field and hence partially neutralize the charges of the plate as shown. The ratio E naught upon E is called the dielectric constant D or relative permittivity of the medium. From electrostatics, it can be shown that E naught is equals to E plus 4 pi I, equation number 4, where I is the induced dipole moment per unit volume, that is I is equals to mu I into n, where mu I is the induced dipole moment in a single molecule and n is the number of molecule per cc. Dividing both sides of equation 4 by E and putting E naught upon E is equals to D, we get D is equals to 1 plus 4 pi I upon E, or D minus 1 E is equals to 4 pi I. Equation number 5. The intensity of the electric field strength X acting on each molecule is calculated by supposing that a unit charge is enclosed in a small spherical cavity which is large as compared with the size of the molecule but small in comparison with the distance between the plates. The electric intensity X is then made up of following parts. Number 1. The field strength of charges on the plate is equals to E naught. Number 2. The charges induced on the surfaces of the dielectrics in contact with the plate is equals to minus 4 pi I. Number 3. The charge induced on the surface of the spherical cavity is equals to plus 4 by 3 pi I. Therefore, X is equals to E naught plus 4 by 3 pi I minus 4 pi I. Equation 6. Substituting the value of E naught from equation 4, we get X is equals to E plus 4 pi I plus 4 by 3 pi I minus 4 pi I is equals to E plus 3 by 4 by 3 pi I. Equation 7. Substituting the value of 4 pi I from equation 5, it becomes X is equals to E plus D minus 1 upon 3 into E is equals to 1 plus D minus 1 upon 3 into E is equals to D plus 2 upon 3 into E. Equation 8. From equation 7 and 8, E plus 4 by 3 pi I is equals to D plus 2 by 3E. D plus 2 or D plus 2 by 3 minus 1 into E is equals to 4 by 3 pi I, or D minus 1 upon 3 into E is equals to 4 by 3 pi I. Putting I is equals to mu I into n as already defined is equals to alpha x into n, because mu I is equals to alpha x already defined. I is equals to alpha into D plus 2 upon 3 into E into n, there, because x is equals to D plus 2 upon 3 E from equation 8. Equation 9 becomes D minus 1 upon 3 into E is equals to 4 by 3 pi alpha T plus 2 upon 3 into E into n, or D minus 1 upon D plus 2 is equals to 4 by 3 pi n alpha. Equation number 10. If rho is the density of the substance placed between the charged plates, that is of the medium between the charged plate, and m is the of its molecular mass, then molar volume of the substance is equals to m by rho. If n represents Avogadro's number of molecule per unit volume, that is n is equals to n by m upon rho is equals to n by n rho upon m. Equation 11. Substituting this value in equation 10, we get D minus 1 upon D plus 2 is equals to 4 by 3 pi and rho upon m into alpha, or d minus 1 upon d plus 2 into m by rho is equals to 4 by 3 pi and alpha. Equation number 12. As all quantities on the right hand side of equation 12 are constant independent of temperature, therefore the quantity of the left hand side of equation 12 must also be constant independent of temperature and depending only upon the nature of the molecule. This quantity is called molar polarization and is represented by P. Further, as applied field produce an induced charge in the molecule by the relative displacement or distortion of electron and nuclei. P is often called induced or distortion polarization and is represented by Pi or Pd. Thus, Pi or Pd is equals to d minus 1 upon d plus 2 into m by rho. Equation number 13th. Induced molar polarization is defined as the amount of polarization produced in 1 mole of the substance when placed between the plates of an electric field of unit strength. From equation 13th, it is evident that the unit of Pi will be same as those of m by rho, in that is molar volume. Hence, Pi is usually expressed in centimeter cube upon mole. Expression 13, giving the relationship between dielectric constant and polarizability, was first derived by Mossotti in 1850 and Clausius in 1879 and is called Mossotti-Clausius equation. Effect of temperature on polarization. Using equation 13, the values of molar polarization has been determination for a mole number of substances. It is found that whereas molar polarization of number of substances such as O2, CO2, N2 and CH4 are constant and independent of temperature, the polarization value for some other substance such as HCl, CHCl3, C6H5 NO2 and CH3Cl do not come out to be constant but decrease with increase of temperature. This observation has been the basis of the measurement of dipole moment and the study of molecular structure as explained below. In case of molecules such as HCl, CHCl3, etc., their centers of positive and negative charges do not coincide with each other. Thus, they possess some dipole moment even in the absence of electric field. The dipole moment thus possessed by the molecule is called permanent dipole moment in the absence of electric field. These permanent dipoles are oriented in a random manner due to thermal agitation as shown. However, in the presence of electric field, two disturbing effects take place. These are: number one, the electric field will tend to rotate and orient these dipoles in the direction of the field. Number two, the electric field will tend to polarize the molecules. If the molecules were stationary, the dipole would have been oriented perfectly parallel to the electric field, that is, at right angles to the plates of the electric field. However, due to thermal agitation, they take up position in between that of the original state and the perfectly parallel states as shown in B for any one permanent dipole. This is case of Thus, in case of molecules possessing permanent dipole, the right side of equation 13 will give the total polarization Pt, which will be the sum of induced molar polarization Pi and the orientation molar polarization Po. That is, Pt is equals to d minus 1 upon d plus 2 into m by rho is equals to Pi plus P naught. As mentioned earlier, the induced polarization is given by Clausius-Mossotti equation through Pi is equals to 4 by 3 pi and lambda equation 15 and alpha. The orientation molar polarization is given by the equation put forward by Debye through P naught is equals to 4 by 3 pi n into mu square upon 3 kT. Equation 16, where U is permanent dipole moment of the molecule, K is Boltzmann constant is equals to R by N and T is the temperature. Substituting the value of Pi and P naught from equation 15, 16 in equation 14, we get Pt is equals to d minus 1 upon d plus 2 into m by rho is equals to 4 by 3 pi n alpha plus 4 by 3 pi n into mu square upon 3 kt. Equation number 17th. Measurement of dipole moment. Number 1. Vapor temperature method. The above equation can be written in the form Pt is equals to A plus B by T. Equation number 18. Where A is equals to 4 by 3 pi n alpha and B is equals to 4 pi n mu square upon 9k are constant for the given substance. This equation is primarily applicable to the gases and vapors. Thus, if Pt is plotted against 1 by T, a straight line graph will be obtained of the molecule possessed permanent dipole. The slope of the plot will be given by B is equals to 4 pi and mu square upon 9k. From this equation, the permanent dipole moment mu of the molecule can be calculated. As all other quantities are constant whose values are known, solving equation 19 by putting the values of the various constant, we get mu is equals to 0.0218 under root b into 10 raised to the power minus 18. The straight line plot for a new few substances with and without permanent dipole, that is polar and non-polar molecules, are shown. It may be seen that whereas Pt varies with temperature for HCl, CH3Cl, etc., possessing permanent dipole, there is no effect of temperature on substance like CH4, CCl4, etc., which do not have permanent dipole and hence possesses only induced molar polarization. Method of measurement of dipole moment. As explained above, the basic equation for the determination of dipole moment is Pt is equals to d minus 1 upon d plus 2 into m upon rho is equals to a plus b t. Equation 20. Where a and b are constant with b is equals to 4 pi n mu square upon 9k. Thus the experiment involves the determination of the dielectric constant d and the density rho at different temperatures t. The values of pt are then calculated and plotted against 1 by t. If pt is found to vary linearly with 1 by t, the substance possesses a permanent dipole moment and the value of the dipole moment mu is calculated from the slope of the line. On the other hand, if Pt is found to be independent of temperature, the substance does not possess any permanent dipole moment, that is, it is non-polar. The dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in vacuum between the plates CO and then measuring the capacity of the same condenser when filled with the given substances C. The dielectric constant of the given substances is then given by D is equals to C by C naught. Equation number 21. Number 2, refraction method. According to Clausius-Mosotty equation, the induced or distortion molar polarization Pt or Pd of the molecules is given by Pi or Pd is equals to d minus 1 upon d plus 2 into m by rho is equals to 4 by 3 pi n alpha. Equation number 22. As d dielectric constant is a pure number, molar polarization P is simply a molar volume of the material. Further, it has already been explained that it is independent of temperature if the substance is non-polar and does not have a permanent dipole moment. For such molecules, it was derived by J.C. Maxwell 1881 that the dielectric constant of a substance is related to its refraction index for light of long wavelength according to the equation D is equals to n square. Equation number 23. Substituting this value in equation 22 above, we get Pd is equals to n square minus 1 n square upon plus 2 into m by rho is equals to 4 by 3 pi n alpha. Equation number 24. Where n square cannot be found by extrapolation to infinite wavelength, the value of refraction index is measured with visible light. This is because visible light can displace only electron, whereas the positively charged nuclei remain unaffected, that the distortion polarization can be considered to be sum of electron polarization Pe and atom polarization Pa star, that is Pd is equals to Pe plus Pa. To find the total value of Pd, it is therefore necessary to measure the refractive index using infrared rays because they can displace the heavy atomic nuclei as well as electrons. But measurement of refractive index with infrared radiation is difficult. Hence, the problem is solved by finding electron polarization by measuring the refractive index n using visible light D line, that is Pe is equals to n square minus 1 upon n square plus 2 into m upon rho. Equation number 25. As an approximation, 5% of this value is added to it account for Pa to get the total value of Pd, that is Pd is equals to Pe plus Pa through 5% of Pe. Then as before, total polarization Pt of a molecule possessing a permanent dipole moment is the sum of the two terms star the first distortion polarization Pd and the second called orientation polarization Po due to permanent moment possessed by the molecule. Hence, we can return Pt is equals to Pd plus Po, equation number 26. Putting the value of Po by equation through, Po is equals to 4 by 3 pi n into mu square upon 3 kt, equation 27th. Equation 5 becomes Pt is equals to Pd plus 4 by 3 pi n into mu square upon 3 kt, equation 28th. Putting the value of constant and simplifying, we get mu is equals to 0.0128 under root Pt minus Pd into T, equation number 29th. Pt can be determined by finding the dielectric constant of the vapor at temperature T, and Pd can be found either by measuring the refractive index using infrared radiation or by approximation method explained above. This method is simpler than the temperature method because it involves the measurement. Number 3, dilute solution method. Equation 20 is applicable to gases and vapors only. For substances which are not gases or which can't be converted into vapors, the following procedure is followed. Number 1. A dilute solution of the given substance is prepared in a non-polar solvent such as benzene, CCl4, CS2, etc. The density and dielectric constant of the solution are determined at various temperatures. Number 2. At each temperature, the molar polarization of the solution PS is calculated using the relation PS is equals to D minus 1 upon D plus 2 into x1 m1 plus x2 m2 upon rho, equation 30, where x1 and x2 are the molar fraction of the solvent and the solute in the solution, m1 and m2 are their respective molecular masses, and rho is the density of the solution. Number 3. The molar polarization of the solution is related to the molar polarization of the solvent x1 and that of solute x2 as PS is equals to x1 p1 plus x2 p2, equation 31st. Thus, knowing the values of x1, x2 and p1, the value of p2, that is molar polarization of the solute, can be calculated. Number 4. The values of P2 obtained at different temperature are plotted against 1 by T. The value of mu is then calculated from the slope of the line as explained earlier. Dipole moment and chemical constitution. Application of dipole moment. The knowledge of the dipole moment of a molecule can be applied in a number of ways to study its chemical constitution. A few important applications of dipole moment are briefly described below. Number 1, in comparing the relative polarities of molecules. For example, the dipole moment of HF, HCl, HBr, HIR 2.0, 1.03, 0.78 and 0.38 dBi respectively. This shows that the polar character of the molecules decreases as we move from HF to HI. Number 2, in calculating the percentage ionic character of a polar covalent bond. For example, the dipole moment of HCl is 1.03 d. If the bond were 100% ionic, each end will acquire full 1 unit charge, that is 4.8 into 10 raised to the power minus 10 ESU. The bond distance in HCl is taken to be 1.275 angstrom, that is 1.275 into 10 raised to power minus 8 centimeter. Hence, if HCl were 100% ionic, the dipole moment would have been is equals to 4.8 into 10 raised to the power minus 10 into 1.275 into 10 raised to the power minus 8 ESU centimeter is equals to 6.11 into 10 raised to the power minus 18 ESU centimeter is equals to 6.11 D. Actual value of dipole moment of HCl is equals to 1.03 d by percentage ionic character of HCl bond is equals to 1.03 upon 6.11 into 100 is equals to 17 percentage approx. Number 3, in predicting the geometry or shapes of molecule, the fact that the dipole moment is a vector quantity and that a practical particular bond that has almost a constant value of bond moment is very useful in predicting the shape of molecule. A few cases are described below. A. Diatomic molecule. A diatomic molecule is always linear irrespective of its dipole moment. B. Triatomic molecule. In triatomic molecule of the type AB2 there are two possibilities. Number 1, the dipole moment of the molecule may be zero, that is in case of CO2 and CS2. This shows that in these molecules one bond moment is equal and opposite to other, hence the molecule must be linear. Number 2, the molecule may have been definite value of dipole moment. Mu for H2O is equals to 1.84 d, mu for SO2 is equals to 1.63 d. Obviously, in these cases, the possibility of linear shape is ruled out. The two bonds must have a definite angle between them, which can be calculated if we know the bond moments as discussed earlier in Section 5.3.1. For example, the bond moment for HO is 1.6 d. The bond angle is calculated to be nearly 105 degree. Thus, H2O may be represented as shown 5.14. Such molecules are called bent molecule and the shape is called V shape. C. Tetraatomic molecule. In tetraatomic molecule of the type AB3, the two simple possibilities are: number 1, the dipole moment of the molecule may be zero, that is in BF3. In such a case, all the four atoms must be in one plane and the angle between the bonds must be equal. Example in BF3 shown. Such a shape is called planar trigonal. Number 2, the molecule may have some definite value of dipole. Example NH3, PF3, PCl3. This indicates that one atom lies out of the plane of the rest of the atoms. For example, the molecule of NH3 may be represented. Such a shape is called pyramidal shape. D. Pentaatomic molecule. The pentaatomic molecule of the type AB4 which we commonly come across are CH4, CCl4, SiCl4, SnCl4, etc. The dipole moment of all these molecules is found to be zero. This is possible only if these molecules have symmetrical or regular geometry so that the different bond moments cancel out each other. The experimental fact confirms that these molecules have tetrahedral shape as represented. 4. In differentiating the cis and trans isomer, the cis and trans isomer are represented as C double bond C HHXX, C double bond C XHHX, trans C. It is clear that the trans form will be non-polar, that is will have zero dipole moment, whereas cis form will be polar, that is will have definite dipole moment. For example, in case of dichloroethylene, putting X is equals to Cl, cis form has been found to have a dipole moment of 1.9 d while the trans form is found to have zero dipole moment. Number 5. In differentiating the ortho, meta and para isomers. As benzene is a regular hexagon and its dipole moment is zero, therefore substituting two atoms or groups in the ortho, meta and para positions, the distribution derivatives will have different dipole moment for the O, M and P isomers as shown. Obviously, the para will have zero dipole moment and meta will have less dipole moment than ortho. Number 6. In supporting the possibility of resonating structure, for example, the nitrous oxide molecule N2O has a small value of dipole moment 0.17 t. If the molecule is supposed to have any one of the following two structure. The dipole moment should be high. This confirms that N2 molecule is a resonance hybrid of structure 1 and 2. Magnetic susceptibility. General introduction to some terms used. Number 1. Magnetic permeability. If two magnetic poles of strength M1 and M2 are separated by a distance r, then the force F acting between them is given by F is equals to 1 by mu into M1 into M2 upon r square. The quantity mu used in the above expression is called the magnetic permeability of the medium between the poles. It is defined as the relative tendency of the magnetic line of the force to pass through the medium as compared to that in vacuum. For vacuum, mu is taken as equal to 1. Similarly, for air, mu is taken as approximately equal to 1. Number 2. Diamagnetic, paramagnetic and ferromagnetic substances. As mentioned above, for vacuum, mu is equals to 1. For other media, mu can be less than or greater than 1. If mu is less than 1, then the magnetic lines of force prefer to pass through the vacuum rather than through the substance comprising the medium. In other words, the magnetic line of force are repelled away from the substance. Such substances are said to be diamagnetic. On the other hand, if mu is greater than 1, then the magnetic lines of force have greater tendency to pass through the substance rather than through the vacuum. In other words, the magnetic line of force are attracted towards the substance. Such substances are called paramagnetic. If mu is very high, that is of the other of 10 raised to the power 3 or more, the tendency of the substance to attract the magnetic lines of force is very high and the substance is said to be ferromagnetic. Ferromagnetism is exhibited mainly by iron, cobalt, nickel, and their alloys. It is a property of greater interest in the subject of physics only. In chemistry, we deal only with the diamagnetism and paramagnetism. The behavior of diamagnetic and paramagnetic substance in a magnetic field is shown diamagnetically. Number 3. Magnetic susceptibility. As seen above, if any material is placed in a magnetic field, the strength of the magnetic field is the material is different from that in vacuum. The strength of the magnetic field thus present in the material is called magnetic induction. If H is the strength of the applied magnetic field and B is the magnetic induction in the given material, the two are related according to the equation B is equals to H plus 4 pi I. Equation number 1, where I represent the magnetic moment per unit volume in the material and is called intensity of magnetization. It may be positive or negative depending upon where the material is paramagnetic or diamagnetic. The intensity of magnetization produced per unit strength of the applied magnetic field is called specific magnetic susceptibility. It is usually represented by chi. Thus, mathematically, chi is equals to I by h, equation 2. It is this quantity, which is usually measured experimentally in the study of magnetic properties of different materials, multiplying the specific magnetic susceptibility with the molar volume m by rho of the material, we get what is called as magnetic susceptibility per mole or molar magnetic susceptibility. It is usually represented by percentage m mathematically. Percentage m is equals to m by rho into I by h, equation number 3. Thus, molar magnetic susceptibility may be defined as the intensity of magnetization induced per mole of the material by the unit field strength. Quite often, it is convenient to deal with the quantity chi m in place of chi. Further, the magnetic induction B is related to the strength of the applied magnetic field H according to the equation B is equals to mu H, equation 4th, where mu is the magnetic permeability of the medium, that is the material placed between the poles. Also, from equation 2, I is equals to chi H, equation 5. Substituting the value of B and I from equation 4 and 5 in equation 1, we get mu H is equals to H plus 4 pi chi H. Mu is equals to 1 pi plus 4 pi x chi 6. Since I in the above discussion is the magnetic moment per unit volume of the material, chi is in fact the volume susceptibility of the medium. However, for most of the practical purposes, we use mass susceptibility. It is obtained by dividing the volume susceptibility by the distance rho of the material. Hence, we have mass susceptibility. Chi dash is equals to chi by rho. Chi is equals to rho chi dash. Substituting this value in equation 7, we get mu is equals to 1 I plus 4 pi rho chi dash, which gives chi dash is equals to mu minus I upon 4 pi rho, which gives chi dash is equals to mu minus 1 4 pi rho. This gives the relationship between the specific magnetic susceptibility and the magnetic permeability of a material of density rho in G by Cc. Since for diamagnetic substance mu less than 1, therefore the specific magnetic susceptibility is negative for such substances. On the other hand, the paramagnetic substance mu is greater than 1, therefore chi or chi dash is positive but small. For ferromagnetic substances, as mu is very large, so chi or chi dash is also very large. Measurement of magnetic susceptibility Gauss method. The magnetic susceptibility are generally determined by the method put forward by Gauss in 1889. It is shows and is briefly explained below. The material under examination is taken in a thin cylinder or a tube, which is then suspended vertically with a wire from one arm of the balance between the two poles or an electromagnet, such that the lower end of the cylinder is nearly in the middle of the poles of the electromagnet. The cylinder is now counterbalanced in the position by placing weight in the other pan of the balance. The current is now switched on into the electromagnet. If the substance is paramagnetic, the cylinder will be pulled down so that more magnet line or force can pass through it. On the other hand, if the substance is diamagnetic, the cylinder will be pushed upward so that the less magnetic line of force may pass through it. In the first case, some extra weights will have to be added into the pan, whereas in the second case, some weights will have to be removed from the pan to restore the balance. Since the change in weight is equal to the magnetic force acting on the material, hence if delta m is the change in mass, then we have delta mg is equals to half chi minus chi a h square, equation 9, where g is acceleration due to gravity, so that delta mg gives the change in weight. The right hand side is magnetic force acting on the material of volume susceptibility chi, and a is the area of cross section and the specimen, h is the field strength, and x a value of chi a is equals to 0.03 into 10 raised to the power minus 6. Thus, using equation 9, the value of x can be calculated. In the above calculation, the above value, absolute value of the field strength H is also required. However, the necessity of measuring H and A can be eliminated if the experimental is first performed with substance of non-susceptibility using the same magnetic field and the same cylinder. For taking this substance, usually water is taken as the standard substance for this purpose. Then evidently we will have delta ms upon delta mw is equals to chi s minus chi a upon chi w minus chi a, 10th equation, where delta ms is the change in mass when the sample under examination is placed in the magnetic field, and delta mw is the change in mass when water is taken in the same cylinder and placed in the same magnetic field. Chi s is the magnetic susceptibility, volume susceptibility of the sample, and chi w and chi a are those of water and air respectively. Magnetic susceptibility and molecular structure. A detailed study of the magnetic susceptibility of a large number of organic and inorganic compounds carried out by Pascal during 1908 to 1913 has revealed that, like many other physical properties such as molar refraction, paracore, etc., the molar magnetic susceptibility chi m is an additive as well as a constructive property. The values assigned to the various atoms and to the structure factor that is double bond, triple bond rings, etc., can be obtained from the experimental determined values for a large number of elements and compound. The values of magnetic susceptibility for some of the atom and structure group are given. Explanation of diamagnetism and paramagnetism. Electron in an atom have orbital motion as well as spin motion as they are charged particles. Therefore, their motion produces a small magnetic field. If all the electrons in the molecule are paired, the magnetic moment of the electron spinning in one direction is cancelled by the magnetic moment of electrons spinning on the other opposite direction. The net result is that the substance has zero magnetic moment. If such a substance is placed in a magnetic field, small magnetic moment is induced in the substance in opposition to the external magnetic field. As a result, the substance is repelled by the magnetic field. This type of behavior is observed for the diamagnetic substance. Thus, diamagnetism is exhibited by those substances which contain paired electron only, that is, no unpaired electron is present. On the other hand, if a substance contains some unpaired electron, the magnetic moment of the electrons do not cancel out completely. Hence, the substance has a permanent magnetic moment of its own. In fact, each unpaired electron behaves like a micromagnet with a definite magnetic moment. If such a substance is placed in an external magnetic field, the micromagnet will arrange themselves parallel to the external field and induced magnetic moment is insufficient to overcome the permanent magnetic moment of the substance. Such substances are therefore attracted by the magnetic field instead of being repelled by it. This type of behavior is observed for the paramagnetic substance. Thus, paramagnetism is exhibited by those substances which contain some unpaired electrons. Determination of magnetic moment of a paramagnetic substance. As explained above, each atom, ion, or molecule of a paramagnetic substance behaves like a micromagnet with a definite inherent magnetic moment of magnitude mu m. When such a substance is placed in the external magnetic field, the micromagnet tends to arrange themselves parallel to the applied field. However, this tendency is opposed by the thermal motion of the particle. Hence, the actual arrangement taken up will depend upon the temperature. In 1905, put forward the following relationship between molar magnetic susceptibility chi m, magnetic moment mu m, and temperature T. Chi m is equals to alpha m into mu m square n upon 3 kt, equation number 11th, where n is Avogadro's number, k is Boltzmann constant, and alpha m is constant for given substances. It represents the diamagnetic molar susceptibility of the substance induced by the applied magnetic field. In equation 11th, all quantities are constant except chi m and t, thus determining chi m for the given substance at different temperature T and then plotting chi m versus 1 by T, a straight line graph will be obtained, the slope of which will be equal to mu m square n upon 3k. Hence, mu m can be calculated. The unit of mu m are Gauss per Gauss. However, it is usually expressed in terms of Bohr magnetons Bm. 1 Bm is equals to 9.2732 into 10 raised to the power minus 21 arcs per. Relationship between magnetic moment and the number of unpaired electrons. The total magnetic moment of any atom, ion, or molecule is the sum of the following two values. Number 1, magnetic moment due to the orbital motion of the electron. It is equal to under root L into L plus 1 Bm, where L is the azimuthal or orbital quantum number for the electron. Number 2, magnetic moment due to the spin motion of the electron. It is equal to 2 into S under root S into S plus 1 Bm, where S is the spin quantum number having value equal to half 1 by 2. If ions or molecules are considered instead of free atoms, it is expected that the orbital motion of the electron are tied into the nuclear configuration of the molecule or the ion so tightly that they are unable to line up with the applied magnetic field. Hence, the magnetic moment contribution due to the orbital motion is negligible. Thus, the magnetic moment of the molecule or the ion is mainly due to the spin motion of the electron. Hence, it is called spin magnetic moment. Thus, we have mu m is equals to 2 under root S into S plus 1 Bm, equation 12th. Here S represented spin quantum number for one unpaired electron for a molecule or ion containing a number of unpaired electron. The expression is usually written as mu m is equals to 2 into under root s into s plus 1 into Vm. Equation 13th, where S represented the total spin quantum number. Thus, for one unpaired electron, S is equals to 1 by 2. For two unpaired electron, S is equals to 2 by 2. For three unpaired electron, S is equals to 3 by 2, and so on. In general, for n unpaired electrons, S is equals to n by 2. Hence, equation 13 becomes mu m is equals to mu under root n by 2 into n by 2 plus 1. Mu m is equals to under root n into n plus 2 Bm. Equation 14th, or thus knowing the number of unpaired electrons present, the magnetic moment mu m can be calculated, or vice versa. The expected value for the magnetic moment mu m for paramagnetic substances for different values of unpaired electron are given. Relationship between molar magnetic susceptibility and the number of unpaired electrons. Taking alpha m to be negligible in equation 11th, as it represented the diamagnetic molar susceptibility of the substance induced by the applied magnetic field, equation 11 becomes chi m is equals to mu m square n upon 3 kt. Equation 15th. Substituting the value of mu m from equation 14th in equation 15, we get chi m is equals to n by 3 kt into n plus 2. Equation 16th. The expected value of chi m for different value of n are given. Application of magnetic susceptibility. Number 1. In confirming the structure of a given molecule, the use of molar magnetic susceptibility in confirming the structure of a given molecule is based upon the fact that magnetic susceptibility is additive as well as constitutive property, as already discussed above. In number 2, in calculation of the number of unpaired electrons in a molecule or ion, knowing the molar magnetic susceptibility chi m, the number of unpaired electrons present in a molecule or ion can be calculated using equation 16th. This has helped in understanding the electronic structure of a number of molecules. For example, the molar magnetic susceptibility of oxygen has been found to be 3400 into 10 raised to the power 6, which shows that it must contain two unpaired electrons. Thus, the structure of oxygen molecule should be represented as OO3. In the study of coordination compounds, the main application of magnetic susceptibility in chemistry has been in the study of coordination compound of transition element. Measurement of magnetic susceptibility helps us to know the number of unpaired electrons present in the complex, which in turn helps to assign the correct structure to the complex ion in some cases. For example, the magnetic susceptibility value of the complex is FeCN6 whole power 3 negative and FeF6 whole power 3 negative suggests that there is one unpaired electron present in the former, whereas there are 5 unpaired electrons present in the latter. These are explained by suggesting the following electronic structures. Number 4. In establishing the formulas of certain compounds. For example, it has been shown that the formula of phosphoric acid is H4P2O6 and not H2PO3. This is because if the later formula were correct, sodium and silver salts NaHPO3 and Ag2PO3 would contain an odd number of electrons and should be paramagnetic, which actually they are diamagnetic. Hence, their salts must have the formulas Na2H2P2O6 and Ag4P2O6 respectively. Similarly, the formula of mercurous chloride is Hg2Cl2 and not HgCl. Number 5. In explaining the existence of odd electron molecule, the compounds containing odd electron are expected to be paramagnetic. This is actually found to be so for a few gaseous compounds, namely nitric oxide, nitrogen dioxide, and chlorine dioxide. Moreover, their magnetic susceptibility show that they can contain one unpaired electron in each case. Number 6, in explaining the formation of a free radical, some highly substituted aromatic compounds have a tendency to dissociate into fragments called free radicals. The existence of free radicals is supported by the fact that such compounds exhibit appreciable paramagnetism, which is explained on the basis that the free radicals contain odd electrons. The measurement of magnetic susceptibility of such substances even helps in calculation of percentage dissociation of the substance into free radicals. For example, the paramagnetic susceptibility of alpha naphthyl diphenyl methyl is found to be 140 into 10 raised to the power 6 minus 6. The theoretical value for a single unpaired electron as shown in table is 1260 into 10 raised to the power minus 6. Hence, percentage of compound dissociate into free radicals is equals to 140 upon 1260 into 100 is equals to 11%. Dielectric properties of solids. Insulators do not conduct electricity because the electrons present in them are held tightly to the individual atom or ions and are not free to move. However, when electric field is applied, polarization takes place because nuclei are attracted to one side and the electron cloud to other side. Thus, dipoles are formed. In addition to these dipoles, they may also be permanent dipoles in the crystal. These dipoles may align themselves in an ordered manner so that such crystals have a net dipole moment. Such polar crystals show the following interesting electrical properties. Number 1. Piezoelectricity or pressure electricity. When mechanical stress is applied on such crystals so as to deform them, electricity is produced due to displacement of ions. The electricity thus produced is called piezoelectricity and the crystals are called piezoelectric crystals. Conversely, if electric field is applied to such crystals, atomic displacement take place resulting into mechanical strain. Thus, such crystals act as mechanical electrical transducer. A few examples of piezoelectric crystal include titans of barium and lead zirconate PbZrO3, ammonium dichloride, dihydrogen phosphate NH4H2PO4, and quartz. These crystals are used as picks up in record players where they produce electrical signals by application of pressure. They are also used in microphones, ultrasonic generators, and sonar detectors. Number 2. Pyroelectricity. Some piezoelectric crystals, when heated, produce a small electric current. The electricity thus produced is called pyroelectricity. Pyre means heat. Number 3. Ferroelectricity. In some of the piezoelectric crystal, the dipole are permanently polarized even in absence of electric field. However, on applying electric field, the direction of polarization changes. This phenomena is called ferroelectricity due to analogy with ferromagnetism. Some example of the ferroelectric solids are barium titanate, BaTiO3, sodium potassium tartrate, and potassium dihydrogen phosphate KH2PO4. It may be pointed out here that all ferroelectric solids are piezoelectric, but the reverse is not true. Number 4. Antiferroelectricity. In some crystals, the dipoles align themselves in such a way that alternatively they point up and down so that the crystal does not possess any net dipole moment. Such crystals are said to be antiferroelectric. A typical example of such crystals is lead zirconate PbZrO3. Uses of above properties of solids. The various properties of the solids as explained above are being used in electronic and magnetic devices such as transistors, computers, telephones, etc.